Hello, and welcome to my talk about understanding the relative strength of QBF CDCL solvers and QBF resolution, which is a joint work with Olaf Beyersdorff. As I assume that not everyone might be fully informed about QBF solvers and QBF resolution, I will just start my talk with some basics to this topic, and then I will go on with our results. Okay. So maybe we just start with a subproblem. Okay, what is a subproblem? We have given a propositional formula phi. Let's call it phi. And we just want to find out if phi is satisfiable. That means if it has a satisfying assignment. If it has a satisfying assignment, we want to return such a satisfying assignment. And if not, if it is unsatisfiable, then we want to return kind of a proof of unsatisfiability or a refutation. Okay. For technical reasons, we will assume that phi is in conjunctive normal form, or short CNF. That means CNF is just a conjunction of clauses, and a clause is just a disjunction of literals. Okay, so for example, this is CNF, which is obviously unsatisfiable. Okay, and then SAT is just the set, or the class of all satisfiable CNFs. Okay, this class is known to be pretty hard because it is NP complete, but nevertheless, SAT solvers, practical SAT solvers, are pretty efficient, at least in on industrial instances. So, for example, in examples from artificial intelligence, for example. So there is a natural question, namely, how strong are these SAT solvers then? Or can we somehow measure their strength? Or can we say why some problems are hard for SAT solvers and why some are not? Okay, let's maybe explain some simple SAT solver. So most of these SAT solvers are based on the so-called Davis-Putnam-Lokman-Laughlin algorithm, or short DPLL. So how does it work? We have a CNF as an input, and the trivial case would be that phi just contains an empty clause. Then this whole formula is obviously false, and we can return false. So it means it is unsatisfiable. If phi, however, is trivially true, that means we do not have any clauses. That means it's a kind of an empty conjunction. Then it's obviously satisfiable with any assignment. So we can return true, which means satisfiable. Okay, and if this is not the case, then we can do what we call unit propagation. That means we search for unit clauses which only contains one literal. So for example, L, the clause which contains only L. And in order to satisfy this formula, we have to set L to 1. Okay, and we just do this. We set L to 1, and then we go on until we do not have any more unit clauses. Okay, when we do not have any more unit clauses left, we can choose an unassigned literal X, and then we just return in a recursive way the case where we set X to 1 and X to 0. Now, let's say phi was unsatisfiable, then it is also unsatisfiable under X equals 1 and under X equals 0. So we will return 0 or 0. So false or false. And if it is satisfiable, then at least one of these two cases where X is 1 or X is 0 has to be satisfiable. So this really returns a correct answer. Okay. the more interesting and commonly more used solver is, however, the conflict-driven clause learning, or short CDCL, which you could say is just an extension of DPLL, with that additionally makes use of so-called clause learning and non-chronological backtracking. So clause learning just means when we somehow get a conflict, we will analyze this conflict and learn a new clause. This is explained a little bit more detailed in the paper. I won't do this here. And then non-chronological backtracking just means we do not have to backtrack to the last decision. So here, for example, if x equals 1 didn't give us a satisfying assignment, then we backtrack back to x equals 0. So this is chronological backtracking, and we can do it also non-chronological by backtracking to some arbitrary point in the past. Okay, both algorithms rely on the theoretical proof system resolution, which I explain later. Let's maybe explain how we can formalize such a CDCL proof. Okay, so I haven't explained CDCL here, but it's basically DPLL with some extras. Okay, so this is the formalization, you could say. So we have 3 sequences. The first sequence is some sequence of T's, and these T's are called Ctcl Trails. I will explain on the next page what these trails are. And from each trail, we can learn a clause with our clause learning procedure. These are the C's. Okay, and to each C belongs a pi, which is just a subproof, a resolution subproof of this learned clause. Okay, so we can extract this subproof directly from the clause learning process. So what are these trails? A trail is just a sequence of literals that represents a CDCL run between 2 restarts or backtracking steps. Okay, we could say that it looked like the following. I distinguish between 2 kinds of literals, namely the P literals and the D literals. So the P literals are just literals, or let's start with D literals. The D literals are just decision literals. So if we go back to the DPLL, we have made some decisions. And here our decisions are these D literals in here. Okay, and these P's are the literals which are propagated by unit propagation. That means we need to have unit clauses with these P's. Okay, so this basically is a trail, and it contains all information we need for such a CDCL run. So this is one way in formalizing such a CDCL, or later also QCDCL proof. Okay, let's explain what resolution is. Okay, so resolution is the underlying system of CDCL, and it basically consists of only one inference rule, namely this one. Okay, where we can derive C or D from C or X and D or X bar. Okay, so C and D are here clauses, and X is just a literal. And we can also formalize a resolution proof, pi, of some CNF phi, which is just a sequence of clauses where each C is either an axiom, that means it's just a clause in the original formula, or it was derived via this inference rule. Okay, and if CM is the empty clause, then pi is obviously a refutation. Also, if we go back here to this proof, the same is true for here. Cm is empty, then also this one is a refutation. Okay. So what are the connections between these SAT solvers and these proof systems? So it's well known that we can extract resolution proofs out of the CDCL. And we can also extract tree-like resolution proofs from DPLL. We can even say that tree-like resolution is equivalent to DPLL, but that's not very important here. Let's concentrate on CDCL because it's a little bit more interesting. So how do we extract a resolution proof from CDCL? Well, we have a proof like this, of these three components. We will just stick together the subproofs pi1 to pi m. So for example, in pi m, we need the clauses, let's say Cm minus 1, then we use the proof pi m minus 1 and so on. We just have to stick them together and get a big proof or a big refutation of this whole formula. Okay. So we can extract resolution proofs from CDCL. That means resolution simulates CDCL. That means we can analyze the SAT solvers at least with the aid of proof complexity. Okay, maybe we do an example here. So there's this very popular CNF, which is called the Pistonhold Principle, PHP, and it consists of the following clauses. You can see it here. And basically, this whole formula encodes the statement that we can put m pigeons into n holes without putting two pigeons in one and the same hole. And obviously, if m is chosen to be bigger than n, then this whole formula is unsatisfiable. Okay, and it is proven that PHP with m equals n plus 1 needs exponential sized resolution refutations. Okay, and then obviously also each CDCL run of this formula needs exponential time. So this is one possibility in finding hard results for CDCL or QCDCL SAT solvers. Okay. Now the question is, what about the other direction? So if we concentrate on CDCL, can we somehow extract CDCL runs out of a resolution refutation? Okay, and there was this result 10 years ago from Pipatsurisavat and Davish. And they found out that for each resolution refutation pi of a formula phi, there is in fact a CDCL run of some polynomial size that refutes phi. Okay, that means these both systems are p equivalent. But there's one point you have to consider, namely this CDCL model in here contains many non-deterministic elements. So for example, decision making, we just said that we have to decide some literals. If we go back to DPLL, we had this x, which was just an unassigned literal, and we did not specify how we find this x or what x do we choose. So this is pretty much non-deterministic, and in here, this decision making depends on the refutation we have given. But if we go to the practice, the CDCL uses, of course, deterministic procedures for things like decision making or clause learning. So we can't really say that choose any decision. So we have to specify this. Okay, so here this result only holds for this partially non-deterministic proof system. And 2 years ago, Mark Vinyals had this result where he proved that this deterministic CDCL with some deterministic decision making is in fact weaker than resolution. Okay, so we get this overview here. we can define a partially non-deterministic proof system, which is P equivalent to resolution, but the deterministic one is really weaker than a resolution, which is not surprising because resolution itself is more a non-deterministic proof system, so it is not surprising that deterministic proof systems are weaker. Okay, so now what we want to do here is we want to lift this whole problem to the quantified level. So we know what happens in the SAT case, and now we want to go to the quantified case. Okay, so maybe let's start to explain what is QBF solving. Okay, so what we do here is we consider quantified CNFs, or QCNFs in short, which is basically just a CNF with some prefix. The prefix is just some quantifiers, which I will write as this. So we have existential or universal literals or variables. And we will assume that, also for technical reasons, that all variables are fully quantified. That means we do not have any free variables in there. And we also assume that phi contains no tautological clauses, because otherwise, yeah, we will just delete them if we have some of these. Okay, and now because our formula is fully quantified, we can just rewrite our aim to we want to check if phi is true or false. So it's not even, we do not really want to know if it is unsatisfiable or not, because it doesn't have any free variables. It is either true or false. Okay, and if it is false, we want to return a refutation. Okay, and this QBF problem is even harder than the SAT problem, because the QBF problem is proven to be a p-space complete. But the same as in SAT solving, industrial instances can be solved efficiently nevertheless. So here we have the same question. So why are some formulas easy, or why are some formulas hard for these QBF solvers? Okay, let's explain the underlying proof system, which is here Q resolution. So Q resolution is just an extension of resolution, which can handle QCNFs. Okay, and it consists of now two inference rules. The first one is resolution, which is basically the rule from the SAT case. But here now the pivot X has to be existential, and we do not have to create tautologies. So if we have an L and C, then the negative of L is not allowed to be in D. And then we have a reduction rule where we can handle the universal literals, where we say that if we have a literal U in a clause and left and right of U is non-existential literal, it's not any, so let's say we have a literal U, and each literal which is right of U in this clause is only universal. Then we can reduce this U. Okay, and we can even more extend this Q resolution system to a stronger system, which is called long distance Q resolution, where we are now allowed to create tautologies. I will not explain this here, but keep in mind that we can also do this, which was introduced by Zhang and Malik 2002. And as resolution, also CDCL can be lifted to the QBF level, which is now called QBF CDCL or QCDCL. Okay, and it was proven that we can extract long-distance Q-resolution refutations out of negative QCDCL runs. Okay, as you see here. Okay, now the question, can we gain a similar equivalence as in the SAT case? Well, there was this result from Janota from 2016, which says that the deterministic or the practical version of QCTCL is really weaker than Q resolution. But we could ask the question, okay, I mean, in that case, it's the same because the deterministic version is pretty weak. Can we at least construct a partially non-deterministic, stronger QCTCL proof system which can simulate Q-resolution refutations? And there we have to say that, well, the original QCTCL and Q-resolution are incomparable, even when we take the non-deterministic version of QCTCL, or the partially non-deterministic version. There are separations in both directions. Okay, so let's make an overview of our results here. So in QBF, we have a more complex picture. So QCTCL is really incomparable to Q resolution. But what we did was we designed a new QCTCL model, which we will call a QCTCL asserting order, no reduction. We will explain this in the paper a little bit more in detail, which is equivalent to Q resolution. Okay, and then we get this overview here. So let's make an example of these separations. So I said we can separate QCTCL and Q resolution. Okay, in the first direction can be done with the so-called Q parity formulas. So the Q parity formula consists of this prefix and of these clauses here, as you can see. And basically you could say that each of these TIs encodes the partial sum of the x from xi1 to xi. Okay, and the whole formula then encodes the statement that the whole sum of these x are 0 and 1, which is obviously not possible. So this whole thing is also false. And we can really write down a polynomial-sized QCTCL refutation of Q parity, which I will not do here because it's a little bit ugly and bulky, but you can do this. Okay, but on the other side, one can prove that Q parity really needs exponential-sized Q resolution refutations. Okay, so this is one direction. The other direction can be done with the help of these Pistonhold principles from the beginning. So then we can construct these formula, which we called trapdoor, which basically consists of a propositionally hard part and an easy part. So the first clauses in here, which are the Pistonhold clauses, are pretty hard to refute, and the rest of this is just some easy stuff. Okay, and you can prove that this trapdoor formula needs exponential-sized QCTCL refutations, but there are constant-sized, you could also say polynomial-sized Q resolution refutations of trapdoor. Okay. And now we want to, so now we have separated these Q resolution and QCTCL, but now we want to design a new system, new procedure of QCTCL that is equivalent to Q resolution. So we have to modify this QCTCL a little bit in order to gain something equivalent. And this modification has to be incomparable, because yeah, well, the original systems are incomparable. So it's not enough to just strengthen the system. And what we do is we use so-called policies to modify this model. So we use decision policies, which just tell us what decision we are allowed to make. Okay, so yeah, we specify rules in decision making. It is still a little bit non-deterministic, so it's not fully deterministic, but yeah, it's still enough. And then we have reduction policies, which tells us how we handle reductions in unit propagations. Okay, so we are in the QBF case, so also unit propagations can make use of reduction. And in our new model, we just say that we do not allow any reduction in the process of unit propagation. And we also use the new decision policy asserting order, which I will not explain here because it's a little bit technical, but basically it's a more liberal system, or no more liberal policy than we had before. Okay, and now our result here is just for each Q resolution refutation pi, there exists a refutation in our new system, QCDCL asserting order and no reduction, of also polynomial size. So these both systems are P equivalent. And then we get this whole overview. So I said DPLL is not so important. CDCL is equivalent to resolution. Then QCDCL is incomparable to Q resolution. Then we have the connection between QCDCL and long distance Q resolution, where we can at least extract long distance Q resolution proofs out of the algorithm. And now we have this new model, so this new QCDCL system, which is really equivalent to Q resolution. Okay, so let's summarize what we did so far. So in the SAT case, we have seen that practical and deterministic CDCL is in fact weaker than the underlying proof system resolution, but the partially non-deterministic model is equivalent. Okay, so we get this overview, and then again the QBF case, it's a little bit more complex. QCDCL is incomparable to Q resolution even in the non-deterministic case, and we have to modify this QCDCL model a little bit, and then this new model is really equivalent to Q resolution, and we get this. Okay. With this, I will end my talk, and yeah, thanks for listening.